Welcome to this explainer, where we're going to completely dismantle your intuitive understanding of space, time, and motion. Have you ever wondered why a ball dropped inside a moving train just falls straight down for the person sitting inside? But someone standing outside on the platform, they see that exact same ball trace out a curved path through the air? Both people are watching the exact same event, yet they describe completely different pictures of what happened. And here's the kicker: neither is lying, neither is mistaken. This strange, beautiful fact sits at the very heart of physics. And today, we're going to unravel the whole shebang.
So let's dive right in with a question you'd probably never thought to ask yourself. Imagine you're taking a sip of water in a car cruising down the highway. To you, that water bottle is perfectly still in the cup holder, right? But to someone standing on the side of the road watching you zoom past, that exact same water bottle is moving at 70 miles per hour. So whose reality is actually correct? The answer, and this literally unlocks the entire universe, is that both of you are entirely correct at the exact same time.
Here is the map for our journey today. We'll be covering the illusion of absolute motion, how Einstein shatters absolute time, spinning worlds and warped space, relativity in your pocket, and finally, the quantum gravity frontier.
Section 1. The illusion of absolute motion. Let's start with something you experience every day to show you how motion is, really, merely an illusion of perspective. Think about this comparison we just talked about. As we established, motion is never an absolute property of an object all by itself. It only makes sense when you specify motion relative to something else, like a specific vantage point. If you choose the perspective attached to the car itself, the passenger is perfectly still. But if you choose the perspective of the ground, the bystander sees a 70-mile-per-hour bottle. It's all about where you're looking from. Now, this specific vantage point actually has a formal name in physics. It's a foundational concept known as the reference frame. You can think of it as essentially an invisible grid that you use to measure position and time from your specific point of view. It's kind of like planting little flags in space and time so you can assign precise numbers to exactly where and when an event happens.
But there's a really crucial distinction we have to make here. What happens when this frame moves at a steady speed in a straight line with zero acceleration? Well, we call this an inertial frame. Inside an inertial frame, the laws of physics take on their most elegant, simple form. Newton's first law, that an object in motion stays in motion, holds up flawlessly here. If you're in a smooth sailing ship or a steady cruising car, you can play catch, pour a cup of coffee, or drop a ball, and absolutely nothing about the physics will reveal your motion to you.
Section 2. Einstein shatters absolute time. So, what happens when the universe's ultimate speed limit violently breaks these simple, comfortable rules of classical physics?
Well, for about 250 years, the Galilean idea of absolute universal time reigned supreme. Basically, everyone believed time flowed exactly the same for everyone, everywhere. But then, in the 1800s, Maxwell's equations predicted that light travels through a vacuum at one single fixed speed. And that created a massive contradiction. Think about it. If you walk forward on a moving train, your speed adds to the train's speed. But light, it doesn't do that. The famous Michelson-Morley experiment proved light speed is constant no matter what direction you're moving. This completely baffled the world until 1905, when a young patent clerk named Albert Einstein realized you just couldn't fix the old rules. You had to completely shatter the concept of absolute time altogether.
By insisting the speed of light is constant for all observers, Einstein mathematically proved that the flow of time and physical length must actually change depending on your relative motion. It's mind-blowing. If a train zooms past you at a high speed, you will literally see a clock on that train ticking genuinely slower than your own. You'll even see the physical length of the train contract. And honestly, the craziest part, two light bulbs flashing at the exact same moment for someone on the train will actually flash at two totally different moments for you standing on the platform. Time, length, and simultaneity become entirely personal.
And this brilliantly illustrates the resolution to one of the most famous puzzles in science, the twin paradox. Imagine identical twins. One blasts off in a rocket to a distant star and comes back, while the other stays on Earth. When they reunite, the traveling twin is physically younger. But wait a second, since motion is relative, couldn't the traveling twin just say the Earth was moving away from her? Why isn't it symmetric? Well, it's because the traveling twin has to physically decelerate, turn around, and accelerate back. That change in reference frames completely breaks the symmetry and makes the time difference a physical reality.
Let's put some real numbers to this, just to show you how dramatic time dilation gets at extreme speeds. If we do the math using what physicists call the Lorentz factor, a twin traveling 10 light-years away at 90% the speed of light returns home a massive 12.5 years younger than her sister who stayed on Earth. The traveling twin experiences just 9.7 years of subjective time, while 22.2 years pass on Earth. Absolutely wild.
Section 3. Spinning worlds, warped space. Now, let's step off those straight-line paths and see what mysterious forces appear when your reference frame starts spinning or accelerating.
Imagine you're on a spinning merry-go-round and you throw a ball to a friend. To you, it appears to curve in the air. That is an illusion caused by a fictitious effect called the Coriolis force. It's not a real physical push, it's just the mathematical cost of doing physics inside a spinning frame. But when you scale this up to the size of a rotating planet, this fictitious force has very real consequences. It literally dictates why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. In fact, back in 1651, Italian artillery officers were thoroughly confused when their long-range cannonballs consistently landed to the right of their targets. Turns out, it was just the Earth rotating underneath the cannonball mid-flight.
Einstein took this realization about non-inertial frames even further, with what he called his happiest thought, the equivalence principle. He brilliantly realized that accelerating in a windowless rocket ship in deep space feels exactly, completely, thoroughly identical to sitting stationary on a planet with gravity. A dropped ball falls to the floor the exact same way in both scenarios.
This astonishing insight meant gravity isn't some invisible tether pulling you down. Rather, it's a direct physical warping of the space-time reference grid itself by massive objects. Things just follow the straightest path through curved space. And amazingly, it means that astronauts in orbit aren't actually fighting gravity at all. By free-falling, they are locally sitting inside a perfect, weightless, inertial reference frame.
Section 4. Relativity in your pocket. If you think this is all just abstract chalkboard math, let me show you how Einstein's theories are quite literally sitting in your pocket right now. Take a look at the daily impact numbers. The Global Positioning System, the GPS in your smartphone, relies on satellites orbiting high above the Earth. But those satellites have to juggle competing relativistic effects. Because they're moving incredibly fast, special relativity says their clock should run slower, losing about 7,000 nanoseconds a day. But on the flip side, because they're high up in a weaker gravitational field, general relativity says their clock should run faster, gaining 45,000 nanoseconds a day. When you combine those effects, the satellite clocks run faster by a net 38,000 nanoseconds a day. And here is exactly why this matters to you. Since GPS signals travel at the speed of light, if engineers didn't intentionally program Einstein's equations into your phone and the satellites to account for that tiny daily difference, your GPS would drift by a catastrophic 10 to 12 kilometers every single day. Ride-sharing, package delivery, airplane navigation, the whole modern world would basically collapse without relativity.
Section 5. The quantum gravity frontier. Finally, we arrive at the absolute cutting edge of physics today, in 2026, where these rules of reference frames face their ultimate and most bizarre test yet.
In classical physics, an observer, like our passenger in the car, is always in one definite, perfectly known state. But modern researchers are now asking a pretty audacious question. What happens when the observer themselves becomes a quantum object? Quantum mechanics tells us that particles can exist in a superposition. That means they can occupy multiple contradictory states all at once. So, imagine an entire reference frame, or a physical laboratory, existing in a superposition simultaneously. Researchers are actively exploring what the universe would look like from the internal perspective of a superposed observer. They're even finding that quantum entanglement itself, that spooky link between particles, might actually change depending on which specific quantum reference frame you're using to measure it.
Right now, brilliant physicists are extending Einstein's equivalence principle to cover superpositions of gravitational fields. They're carefully defining quantum reference frames to handle subatomic particles that exist in multiple mass states at once. By pushing the idea of the reference frame into the quantum realm, scientists are hoping to finally bridge the impossible gap between quantum mechanics and general relativity. It's the holy grail of modern physics for sure, a complete theory of quantum gravity.
What beautifully unites all of this, from Galileo's simple ship to Einstein's curved space-time, all the way to quantum superpositions, is this profound realization. There is no absolute floor to the universe. Every single observer, no matter how they're moving, has an equally valid perspective of reality. The universe isn't a fixed stage, it's a highly dynamic web of relative perspectives.
We've completely dismantled the illusion of absolute motion today, showing you how space, time, and gravity bend around the observer. But as researchers continue to probe the quantum universe at this very moment, what mind-bending illusions of space and time will we uncover tomorrow? When the final theory of everything is written, how will it completely rewrite your intuitive understanding of reality next? Thank you so much for exploring the secret language of motion with me in this explainer today. Keep questioning your perspective.